Welcome to another GC Basic tutorial demonstration. This is part 9 for the PIC18xxQ20 chip family. Okay, let's do the preamble. Please subscribe, like, make comments, let the video run all the way through, subscribe. Just need all that to make some revenue, okay? Otherwise, I'll keep begging for GC Basic donations throughout the year. Okay, let's get started. We are now in video 9. We're going to use a timer. We're going to do a timer overflow. We're going to use an 8-bit timer, 16-bit timer to flash the LEDs. We've seen this stuff before, okay? We've seen the flashing of the LEDs, and I'll recap that. So what we're looking at in the tool chain here is that essentially GC Basic simplifies the use of using timers. You have a few commands. You can use calculators and all sorts of things. It just makes it a lot easier to use. Let's just have a look what we've got. I've got a prototype board. It's got some circuitry on there, powered up 5 volts, programmer. I'm using a PIC18 still. Serial port is attached. I've got some LEDs with suitable resistors, a potentiometer, and a switch. What does that look like? Let's look on desk cam. Oh, I've been working here. I've got a scope plugged in there. Look. Okay, bit of a PIC3 there. Okay, so what have I got here? Let me zoom. I've got the Q20 sitting here. It's connected through. This is the programming flying lead here. Then I've got some LEDs that are rotating. Now this is program 4040. We're just going to use this as the base. So it's doing what I programmed it with 040. I've got a switch which is doing nothing, and a set of potentiometers. They're not doing anything in this because all we're going to do is use the timers to sequence the LEDs. Okay, so I can zoom in on that, and that's as far as we need to go, really, to be quite frank. Don't really need a lot more today, because all we're going to do is take out a command we've seen before. Okay, let's have a look at what this time is all about. So timers generate accurate delays based upon an oscillator, and that oscillator currently is the internal oscillator, and we've been using the wait command, which is an internal calculated delay feature of GC Basic, and we saw that earlier on. We can have different delay features and time schedules. Now, if you wanted to have very accurate, you'd use an external oscillator, and that external clock will generate some very tight loops in terms of the timers. Now, the timer is part of the CPU, and it's operated using something called a pre-scaler and a post-scaler, and we'll look at that in some detail. But a timer is no more than just a binary counter. It can be configured to count things. It's either internal or external. We've been using the internal oscillator so far, but you could use an external oscillator. The registers internally all increment to specific values, and once they meet a specific values, if I talk about the overflow, it generates an interrupt if enabled. And this diagram we can see on the screen here is one that we see sometimes inside of the data sheet, but I'm going to explain it a bit better. So what we've got is some way of figuring out from the frequency of these oscillators, internal or externals, we need to control the timer. And so in GC Basic, we say initialize the timer, and we say what the oscillator source is. We tell it the pre-scaler and the post-scaler, and then we tell it what the clock source is, or the parameter that's required. And we start the timer, and then we set it to a value. And we have calculators that you can use, and these calculators are within the installation. You just go to the particular folder, and these spreadsheets all exist so that you can figure out, you can put the clock megahertz in, you put in the pre-scaler, the source divider, which is this third parameter, and then it's the post scaler, and it works out exactly how long it will take and what values you need to use. We're not going to use that today because I've done that calculation before, but this is essentially anything in orange you put in and you get the yellow out, okay? Really quite simple. Let's look at this diagram at the bottom now in detail, because this is what it looks like in the data sheet. It says here you can have your clock sources, and we're going to select the clock divider of 4. That's the clock frequency divided by 4. We're going to set the prescaler. We're going to set a register called T0CKPS. We're going to mask that. It goes through a whole series of sequences, and it says, am I using a 16-bit register or not? Then we've got the post scaler, and then we've got this overflow over here on the right-hand side. It's complicated because all it's doing is the following. It's saying we have an oscillator, an oscillator source is generating a square wave. That square wave is scaled. And why do we need to scale it? Because you need to get these clock sources into the range that you require. So prescaler might expand the clock out, expand or increase or decrease the frequency. You can post scale it, and you can make it even longer. So you've got a larger range because an external clock source, think of it as being extremely high frequency. We're going to lower the frequency and then count that lower frequency. We're going to enable the timer. Then we're going to set the timer counter value. And I've set it to B1 as a random number. And then what it will do, it will increment that. Once the timer has been enabled, it will increment the timer. And once it goes to some value that is called 255 or FF, a special event occurs. It resets the counter to 0 and an overflow occurs. At that point then, if you have the interrupt enable flag set, you get an interrupt signal. Very simple. So what we've got is a clock on the left-hand side. We're stretching the clock out into the range that we want to use. We use that new frequency to increment our timer. Once it becomes 0, we generate the interrupt. Let's have a look at some source code. And we're going to look at that source code. We've got this timer 0 overflow, an 8-bit, and a 16-bit timer. All very similar, but as I said earlier on, I have preloaded this chip with this program, and this program, I'll shut every other program so we know exactly what we're doing. I have gone back to 040, and all it's doing, as you saw on the desk cam, is rotating the LEDs back into here. Let's zoom in for you. Let me just click on the screen. There we go. I wasn't clicking on the screen then, by the way. Okay, great. Close that down. We're going to open up 110, 120, 130 eventually, but let's just start with 110. Control B, get rid of that. Let's just collapse everything down by hitting Control A, Function key F2, fold, type in fold all, and it will just fold everything down. So let's look at our source code, shall we? We've seen this many times. We've defined the constants exactly as we were previously. So we've got exactly the same constants. We don't need to review those. But essentially what we've defined the LED 7, 6, 5, and 4, and we've set them to out. So we've defined those in our little diagram. We should cover the code. I've defined some constants. Ports C.7 to C.4 are our LEDs. And then I've set those to out. These other ones are just there for consistency from the previous demonstrations. Here's the main program. Because I need a value, I need a variable, I've called one called timeout. And I'm going to use a 16-bit timer Now, why am I using a 16-bit timer? Is because I just want it to be a bit longer. I need it. An 8-bit timer has a very short sequence, 0 to 255, and therefore my post-scalar and pre-scalar numbers are more difficult. I just don't get the range, and I'll show you that in a moment in the 8-bit timer. I just don't get the range. And so what I've done, I've used a tool, and that tool is called, one I've used is called Mr. Timer eHelper. There's a spreadsheet that we've got, and I've set the oscillator to the internal oscillator. I've set the pre-scalar to 64, the post-scalar to 1, and I'm using the clock source divided by 4. And that is quite a common way of doing it, and we can look at that. If I look at this calculator, and I get a value of 0BDC. I'll show you that in a minute. And I've said here, set timer 0 to that value. And then, fantastic, I've got this new command we're introducing here called onInterrupt. And we can say onInterrupt, timer overflow, call something called blink. And that is the complete command to manage the overflow of timer 0. OnInterrupt is it will insert all the correct code for us. When this event occurs, timer overflow, call a program called callBlink. Let's look at callBlink. All callBlink does is set timer 0, the variable, to the number 1 because the event has occurred. And we're going to test for that in our main program. And then you can clear the timer overflow. Now I've added this here for clarity. In actual fact, GC Basic automatically clears that event for you once you've handled it. So once you've handled that event, it will automatically clear this, but I put it in here for clarity. Okay, now let's go back to see what our program is actually doing with all this. Well, we're setting the LED to 1. We've seen this before. If the timeout equals 1, that means the timeout has occurred. Rotate the LEDs. We've seen that from previous programs. We then set the timer to, we set our variable back to 0, and we set the timer back to its original number for 1 second. So what we've got is a way of setting the timer, calling a subroutine that sets a variable, and in our main program, all we're doing is saying, has that event happened? And it is a good practice to do it this way. You could put some of this code inside the interrupt subroutine. Bad practice. Because as you extend that interrupt out, you'll start missing interrupts. This way, the main body of the program is handling the interrupt. Let's program this and see what happens. Function key F5 I've pressed to program it. It's now compiled it, and we'll go out to deskcam. We can see it's running. And we can see it's running per the value that we put in our program of this one here. Now, be very careful. I should have said this at the top. The frequency that this value is set on should have been for 16 megahertz. Hence, it's running quickly. I was playing with that earlier on. So if I just reprogram that, look at deskcam, because that's not a delay of 1 second. This is a delay of 1 second. That's better. There we go. So I've calculated the frequency at 16 megahertz. Let's have a look at how we're doing that. If we go out to my folders, I'll zoom in for you. There is, I'll zoom in even more. How about that? There we go, look. There's a set of calculators in here. And those calculators, you can unpack those into your folder. So I'm extracting those into the default folder, and it will open my default folder for me. After a few seconds, it will actually have unpacked them. As you can see, it's unpacking them now, and it will open the folder. And in here, there's a whole series of timers. You can use those timers to calculate things. So if you come into timer calculator, I'll just put that in front of the window for us. I can select my chip, PIC18. I can say my frequency is 16. I want a 1 millisecond delay. And here is the value we're actually using here. Look, 0BDC. 0BDC. Let's go back to our source program. 0BDC. That is calculated. So if I want to set it at 16 megahertz to a different frequency, I can come back into here and set it to 2000. I would set that value. In actual fact, it's changed the preloader. Look, it's changed the prescaler here to 128. It was 64 before. So we have a way of calculating delays. These are tools that are available. They're within the installation. So I've done that for most of the calculations we're using today. So this particular one that's on the screen now is using a 16-bit timer. And how do I know that? Is because I have this constant set. And why have I got that set? Let's go back to PowerPoint. We look at this particular slide. There it. We just need to. Oh, so sorry. We just need to set this constant here in the middle. I'll put my pen on so you can see it. I'll just do that again. I'll do that properly. It sets this one, so it says it's got a larger range. And now we're going to look at what actually happens when we change the timer type. So if I go into number 120, 120 is an 8-bit timer. Close that down. So an 8-bit timer doesn't have that constant. Same construct to initialize the timer. What is your clock source? What's your prescaler, postscaler, and what's your clock divider? Same start timer, but the largest value I can put in here is FF or 255. So this is every 10 milliseconds. The range is not that high. So what I'm going to do this time is when I call my overflow, when my overflow occurs, or when a counter occurs, I'm just going to count it 100 times to make it into 1 second. Let's have a look at that in code. So there's no interrupt on this one. All I'm doing is saying, wait for the interrupt flag to occur, clear it manually for clarity. Now I'm doing this because we're not using an interrupt. So I'm saying, wait until the interrupt flag occurs. How do I know what the interrupt flag is? Function key F4, open up PICInfo. PICInfo is opened. Let's zoom in on that. There we go. I've got the correct chip selected. If I press the interrupt tab, I'll zoom in on that for you. Here are all the interrupts available on this chip, and there's quite a lot. And so what we're doing here, we're looking for timer 1 overflow. Here it is. Oh, so sorry. Timer 1 overflow. The flag, the enable flag, the enable bit is TMR0IE, and the overflow is TMR0IF. And that's exactly what we had in our source program. Same constant. So if I just take a copy of that for a second, just to show you it's the same copy, put it in here. There we go. So you don't have to wade through the data sheet. You can actually use PICInfo to show you these different interrupts. And there's quite a lot of these interrupts that you can actually test against. So that flag will roll every time there's an overflow. So we say here, wait whilst it's 0. Therefore, the moment it becomes 1, it will then increment to here. So it will repeat on that wait. We're going to increment that variable timer counter to 100. So we increment it every time. When it's 100, rotate the LEDs and set the variable back to 0. And finally, set the timer. Let's have a look at that in our source code. Set the timer. So what we've got is a very simple program in here. Wait for the event, clear the timer, increment our counter. If it's 100, therefore 1 second, do something, but always reset the timer because we have to put it back to 10 milliseconds. Compile. Function key F5 is what I pressed just then. Desk cam. So this time, we're not using an interrupt, we're using the interrupt flag. There we go. And it must be doing it because it's doing it. Look at the 16-bit timer. 16-bit timer, program 130. Very similar. Very similar, apart from the initialization, because in the program here, if you look at the program, I haven't got that counting going on. Because I can wait until this flag is set, because the period is much greater when I'm using a 16-bit timer. And so I've set it to every 1 second. So I'm saying here, wait until this flag occurs, but this is what's called a blocking transaction. The program will sit here on that wait while until that flag occurs. So it won't do anything else. It will just loop around in there. When that event finally occurs and that little bit has been set to 1, it will come through our program and it will toggle the LEDs. How do we go about setting it up? Very similar. We set the scale, we set up the interrupt with the pre-scaler of 64, post-scaler of 1, and the clock divider of 4, start the timer, and we set it to a value of 3036, which is binary. We have binary 0, does it? Yeah, there you go, binary BDC. If you hover over it, it will show you it. So this is not using an interrupt. Again, we're using this flag, which creates a blocking program. Function key F5 to program. We go out to desk cam. We will see no different. We're just using a different approach, a 16-bit timer rather than an 8-bit timer. So what have we seen? We've seen that timers can be rather complex in this diagram, but we've seen them that we can actually make them work quite easily because we can check the flags within GC Basic. Next time, we're going to move on. We're going to look at the EEPROM. We're going to show some values on the serial terminal. We're going to read it in and out. We're going to write to the EEPROM, and we're going to see that in terms of putting it on the serial terminal, but we can look at it within our programmer as well. So, timers sound hard. It's a bit of a longer video, but thank you for staying with me. Like the video, etc. Enjoy.